Here's our warm-up question for 3.4, the last topic in Unit 3. So let's suppose a person is jumping on a trampoline. At the point that the person is in midair, like we see right here, we want to know, would the person be weightless, would the person weigh more than usual, or would the person's weight be unchanged? Take a second to answer this in your bell work packets along with a brief explanation, and then we'll proceed onward with our lesson. So today we're looking at 3.4, apparent weight, okay? Some announcements real quick. Unit 3 notes, bell work, late work, and review will be due Tuesday, November 17th. And then the Unit 3 test will be on Tuesday, November 17th as well. Monday will be used as a review day for you guys to work on review packets. So what we're up to today. Learning the physics behind perceived changes in weight in the sensation of weightlessness. And how can we mathematically model these apparent shifts in weight? All right, so here's a little scenario that we would do in a typical year, so we'll skip over this here, okay? So please recall, okay, that weight depends on two primary factors, okay? The mass of an object and the acceleration due to gravity, okay? So we need to ask ourselves, if our weight changes in midair, are any of these factors changing? Does the mass change, or does the acceleration due to gravity change? So we know the mass doesn't change, hopefully not. That means we lost a body part somewhere along the way. And we know the acceleration due to gravity is not changing because, as we talked about back in Unit 2, the acceleration due to gravity is the same on the surface of a planet for all objects, okay? So that tells us that our weight is in fact the same, okay? The weight of an object on a planet never changes. So what causes our person to feel weightless when they're in midair, okay? So what causes the sensation that we feel of weight is actually the normal force, okay? It causes us to feel what we call our apparent weight, okay? So for a person who's in midair right here, okay, they still have weight, they still have that force due to gravity pulling them down, hopefully, otherwise they'll float away, okay? But they're not going to feel their weight because there's no normal force pressing against them from the surface. When they land back on the surface, they'll feel the normal force there, and thus they'll feel their weight again, okay? If we consider a person on an elevator, if you've ever been on an elevator, when an elevator first starts gaining speed, okay, you'll feel yourself get a little bit heavier as the elevator gains speed and goes upward, and that's because you want to stay at rest. You want to stay where you're initially at, and so as a result, you're going to press more against the elevator floor, which means the normal force is going to increase against you. So the normal force is going to grow stronger, and that's going to cause you to feel heavier than you actually are. Your force due to gravity remains the same, but your normal force remains the same. Likewise, when your elevator begins to slow down, okay, you're going to gradually lose contact with the elevator floor because you want to keep moving upwards while the elevator wants to slow down and come to a stop. So you'll lose a little bit of contact with the floor, and thus your normal force will shrink, and you'll feel lighter than you actually are. We can actually see this real quick with a real quick demonstration here that I can pull up on my computer. All right, so we can see right here that if this person goes upward, they're accelerating and they feel heavier than normal, and the normal force is 11,004 newtons, okay? Now we can see when their acceleration is negative, okay? We'll go through this again. So again, the force due to gravity never changes. The normal force increases, they feel heavier when they're accelerating positively, and then when they're accelerating negatively, they feel lighter because their normal force has decreased. Again, that goes back to the idea of they're losing contact or gaining contact with the surface, which causes them to feel more pressure from the surface and make them feel like they've gained weight. Okay? Boop, 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 boop. Let's see here. So when our person is in midair, there's no normal force acting upon them, so they're not going to feel that sensation of weight. Okay? So here's a chart that captures the main ideas that we need to have. So if our acceleration is 0, meaning we're either at rest or moving at constant velocity, the normal force is going to be equal to our weight because we're in a state of equilibrium, meaning the normal force fully supports our weight, okay? If our acceleration is greater than 0, okay, our normal force is going to be greater than the weight of the object, so we're going to feel heavier than we actually are, like in this case right here, where our acceleration is positive, greater than 0. And then lastly, if our acceleration is less than 0, okay, our normal force is going to be less than our actual weight, so we're going to feel lighter than we actually are. So when our acceleration is less than 0, we're going to feel lighter than we actually are. And then lastly, if our acceleration is the acceleration due to gravity, we're going to be in a state of free fall, like we were in the trampoline, and we're going to feel like we are floating. In fact, we'll feel like we're floating, but it's not that we're actually floating. It's just that the elevator is falling at the exact same rate as us, so we can't perceive the elevator as moving, so we feel weightless. There's still the force due to gravity pulling us down, but we can't perceive that because we're now in a state of free fall. We're not in contact with anything. There's no normal force acting upon us. And so the same thing happens in a trampoline. In the trampoline case, when the person's in midair, they're in a case of free fall. The force due to gravity is still acting upon them, but because there's no normal force there, they can't feel that sensation of weight. So now let's look at a think, pair, share here. A car is heading to the right and gaining speed. Draw vectors for velocity and acceleration. Based on this diagram, is the acceleration positive or negative, okay? So our object is going to be heading to the right, okay? So our velocity vector will point to the right. And then because we're speeding up, again, if we speed up or gain speed, that means our acceleration vector has to point in the same direction as our velocity vector. So our acceleration will also point to the right. So it would be a positive acceleration, okay? If we were to slow down, all right, our acceleration vector would have to point the opposite direction of our velocity vector. So if our velocity points to the right, our acceleration would have to point to the left. Again, like brakes on a car pushing against us in the opposite direction, okay? So now we want to know, will the person feel heavier, lighter, or the same? Justify in 1 to 2 sentences, okay, from the perspective of normal force. So what's going to happen here, okay, is because the acceleration is positive, our car is speeding up, okay, we're going to feel heavier, okay? So what's happening is we want to stay at rest or at our current state of motion inside the car because there's no force acting on us. The force is acting on the car, but not on us inside the car. So as a result, we're going to stay in our current motion, and the car is going to come up from behind us. The seat's going to come up from behind us and press us and keep us going forward. So that's why I feel like we're getting thrown back in our seats. But when that happens, the normal force increases on us because the seat is pressing now against us more when we speed up, and that's going to make us feel heavier than we actually are because we now have an increased normal force acting on us. So if you've ever wondered why you feel heavier when a car begins to speed up, why you feel like you're pinned to your seat, it's because a combination of 1, your inertia to stay where you originally were, and 2, the normal force pressing on you from behind, making you feel like you're heavier than you actually are. So let's look at some examples here of mathematically modeling apparent weight. So a 70 kilogram person, let's just say 70, not an. This should say a 70, not an 70. So a 70 kilogram person is standing on an elevator that's ascending a building when it begins to slow down at a rate of 6 meters per second squared. What would the spring scale underneath the person read during this moment? So there are 3 steps that we need to do these types of problems. For 2 of the steps are pretty normal to us, free body diagram, Newton's second law. But the first step we have to do is we have to determine the acceleration of the object. Is it positive or negative? So we need to know, is this going to be positive or negative? So at first glance, because it says we're losing speed, we're slowing down, people might think we have a negative acceleration. But again, we need to think about which way is our object heading? What is the velocity of our object? Are we heading up or heading down? And then are we gaining speed or losing speed? Okay, because that will tell us our acceleration, the sign of our acceleration relative to our velocity, okay? So, all right, if we look right here, for example, in our first step with this example, since we're descending, we're going to draw a velocity vector that's going downwards, showing that our elevator is going downwards. And then because we're slowing down, we're losing speed, that means our acceleration has to be pushing up against us in order to slow us down and bring us to a stop. So the acceleration has to be pushing up and thus be positive, okay? So now the second thing that we're going to do is we're going to draw a free body diagram, okay? Like we can see right here, there's going to be 2 forces that are acting in these apparent weight problems. The normal force and the force due to gravity. So in these apparent weight problems, these are the only forces that are going to be acting, okay? So now what we do is we use our free body diagram as a map to sum together our forces in the y direction. All right, so our net force is going to be the sum of forces in the y direction here, so that's going to be normal force, Fn acting upwards, and then minus Fg because the force due to gravity is acting downwards. So Fn minus Fg. And so now what we do is by Newton's second law, we know this net force is equal to mass times acceleration. So we have Fn minus Fg equals m times Ay. Okay? So now what we can do is substitute mg for Fg. The equation for the force due to gravity is mass times the acceleration due to gravity. So we're going to have normal force minus mass times the acceleration due to gravity equals mass times our acceleration. Okay? So now we can start plugging in numbers. Our mass is 70 kilograms. Our acceleration due to gravity is 10 meters per second squared. And then our acceleration, our AY, is 6 meters per second squared. Okay? Please note that the acceleration, if the acceleration was negative, this would be a negative 6 right here. Okay? But it's positive in this case, it's positive. Okay? So 7 times 10 is going to give us 700. So we're going to have Fn minus 700 equals 420. We add 700 to both sides, which is going to give us Fn equals 1,120 newtons. Okay? So we're always going to be solving for a normal force in this case. So what this tells us is if we were looking at a spring scale in this case, like ones you see in bathrooms or ones you see at grocery stores, this spring scale would read a weight of 1,120 newtons. Now this doesn't mean the actual weight of our person is 1,120 newtons. It means that the normal force that's read by the scale is 1,120 newtons. And so we can see that this makes us feel heavier than we actually are because our actual weight of the person is 700 newtons, whereas our normal force is 1,120 newtons. So it makes us feel heavier than we actually are. All right, so here's a check for understanding if you would like to do so. Okay. You can pause here and we'll pick up here after you've completed this check for understanding. If you need help, you can proceed through the remainder of this video where we'll walk through this problem together. So, an 80 kilogram person is standing on an elevator that is ascending a building and is speeding up at a rate of 3 meters per second squared. We want to know what would the spring scale underneath the person read during this moment. So one, we first got to determine if the acceleration is positive or negative. So in this case, we're ascending, meaning we're moving upwards, so our velocity is going to be a positive arrow. Okay, and then because we're speeding up, that means our acceleration has to be in the same direction as our velocity, so our acceleration is also going to be an upwards arrow. So our acceleration, in this case, A, is positive. The next thing we do is we draw a free body diagram of our object, which again is going to be the same as we've seen before. So we have the normal force, and we're going to have the force due to gravity. Okay, and then lastly, we use Newton's second law to determine the normal force. So again, we have F net y, which is going to consist of the normal force minus Fg based on the free body diagram, and that's going to be equal to mass times the vertical acceleration, may. So as a result, we're going to have Fn minus mg, or minus Fg equals may. So now we can replace Fg with mg. The force due to gravity is equals mass times the acceleration due to gravity. Okay, so that's going to give us the normal force minus 80 times 10, where the 80 we got from replacing m with 80, the mass of our object person, and g we got from replacing g, or 10 we got from replacing g with the acceleration due to gravity. Okay? So we have Fn minus 80 times 10 equals 80 times 3, 80 again being the mass, 3 being the acceleration of our elevator, not the acceleration due to gravity. Please don't confuse the two. So we're going to have Fn minus 800 newtons equals 240 newtons, or that the normal force acting on our person is 1,040 newtons. And this is our lesson for 3.4, apparent weight.